Welcome to the fifth part of the Introduction to Haskell course, and in this part we're going to be talking about list comprehensions and higher order functions. List comprehension is a very useful and powerful method of creating new lists from existing ones. The general syntax is described here. So we have open brackets, as in signifying a list. Then we have a generator separated by a vertical line, and then element taken from this list. So a left arrow and the list, and finally an optional guard. So let's see what all of these terms mean. The generator is the expression that specifies how the new list elements are calculated. So the generator will be what the actual values in the new list will be. The element is a single element from the initial list, so from this list. And the guard is a condition that must be satisfied by this element from the list to be considered as a generator. Okay, so the whole syntax here can be read as create a new list by applying the generator for each element of the list that meets the criteria set by the guard. Let's take a look at some examples of list comprehensions to get a better understanding. So in the first example, we want to create a list that contains only the even numbers. So we have an initial list and we want to take only the even numbers from that list. In this case, we use x as the generator, where x is taken from this initial list that we defined here as the numbers 1 through 10. And then we have a predicate that the x element must satisfy to be considered as a generator, and that's that the number x is even. So we apply the even function to x, and this guard always must be a Boolean expression, so always must equate to either true or false, which is exactly what the even function does. And the result is a new list of only the even numbers from the first list, which was 1 to 10. Now we have only the even numbers from 1 to 10. Okay, so the next example is pretty much the same, except I want to show here that we can, besides using the generator as is, as just an element from the list x, we can also apply functions to it to tell Haskell how to calculate new values for the new list based on the elements of the old list. So here we, for example, double all the even numbers. We still have the same predicate, so we check for even numbers, but in the new list we double each of them. Right, so we can apply functions to the generator or in the generator clause. And the third example shows that generator does not have to include the element. So we can just use the element as a checking of a predicate, and we can create a completely, different value for the new list. So for example, here in the generator, we just put a static value of a string even, and if an element from this list, an element x, satisfies this predicate, then the generator will be triggered, and the generator value will be included in the new list. So we'll have 5 of the same values in this case, and we do not use x as a generator at all. List comprehensions are very versatile, so we can work with multiple lists and multiple guards to create the new list. If we use multiple lists, then the deeper nested lists in the definition will be iterated through for each element of the previous lists. To show an example here, we have a list comprehension that generates a tuple value, okay, x and y, where x is taken from the first list 1, 2, 3, and y is taken from the second list from A to C, so ABC. And we can see that in the result, the first three elements of the new list all have the same x value, 1, right? And the y value is iterated through, so 1a, 1b, 1c. Then for the second value of x, y is again iterated through, 2a, 2b, 2c. Okay, so the iteration goes as x1, y1, then x1, y2, and so on. Right, so the deeper nested list, deeper nested being the ones further to the right, are iterated through for each element of the previous list. And with multiple guards, it's simple. It's just that each has to be satisfied for the generator to trigger. So in this example, we have the same even numbers list comprehension from 1 to 10. We check that the number is even, but we also check that the number is greater than 5, for example. So we have two guards, and both of them must be satisfied for the generator to trigger. And in this case, we only get the numbers 6, 8, and 10, as those are the only even ones and greater than 5. Now we get to higher order functions. So in general, higher order functions are functions that take other functions as arguments. So we already saw this in the previous video where we looked at the function operators, and specifically the function composition and function application both accept a function as an argument. So strictly speaking, they are also higher order functions. And here we have a function to apply a given function twice, right? So to signify a function as an argument, we use the parentheses and then the normal function type signature. So from one type to another type, in this case, A to A. And our function accepts a function that goes from A to A, accepts the argument A, and finally applies this argument to the function, in this case twice, but in any case it produces again A. So the definition is apply twice, we accept the function as f, we accept the argument as x, and we apply f to x, and then again we apply f to the result of that application. So apply twice, and here we use partial application or currying. So with plus plus and then a string, we know that plus plus is the operator for list concatenation. So it takes in two lists and returns their concatenation. In this case, we apply it to only one argument. So it's a partial application. So this is a function now. This whole thing is a function that accepts another list to join them together, right? And then we supply that second argument here, and then this first function is applied twice to it, right? So we have 1 plus plus 2 plus plus 2. That's the result. Now we'll look at two important, or what I consider very important, higher order functions in the prelude. The first one being map, which is, I think, the most important one. It's a function for working with lists. And what this function does is apply a function. So it's a higher order function. It accepts a function and applies it to each element of a list. So since we have just covered list comprehensions, we could define this function using list comprehension. In this case, we know that it accepts a function. It accepts a list to apply that function to, and it gives a result which is a new list with all the elements resulting from the application of this function to each of the elements, right? So the type signature says from A to B, and then accepts the list of A's. So it has to be a list of A's because the function accepts A's as an argument and gives B as a result. And then we get finally a result as a list of B's. Of course, type variables A and B may represent the same type here because there is no class constraint, but it's just defined as polymorphic because we could go from, for example, a function could take in a number and return a string, and then if we apply this function to each number in the list, we would get back a list of strings. So the types could be different, but again, could be the same. So how would we define this with list comprehension? We take in the f as the function, we take xs as the list, and we apply the function f to each element x taken from this list of xs. So if we take an example with our square GT100 from last time, the function we defined in the last video, we end up with a list of booleans, right? Because this function returns a boolean, either it's greater than or it's not. And then if we map this function to a given list, we get back a new list with the elements being the result of the function application. So square GT100 applied to 7 returns false, to 8 returns false, 9 returns false, 10 false, and then finally 11 and 12 equate to true for this function, and that's what we get in the new list. Here we have some other examples using the map function. So always the pattern is the same, right? We accept a function and we apply it to some list or to each element of the given list. So in this case, this function is multiplied by 2. So every number in the list 1 to 5 is multiplied by 2. We get back 2, 4, 6, 8, and 10. We can map the not function, which takes in a Boolean value and reverses it, right? So not true is false, not false is true. So that's what we get in the result. We can map the reverse function that takes in a list and reverses the order of its elements. So we know that strings are actually lists of chars, so this works with strings. And then each element, so not in this case, not the list is reversed so that we have Ada and Cardano, but each of the elements is reversed because map applies this function to each of the elements. So reverse apply to Cardano and apply to Ada. Of course, with Ada, it stays the same because it's the same order, but the Cardano string is reversed here. We can also have some function. This is again using partial application of the plus plus operator, and then we apply it to the function to concatenate the strings, so we get hi Joe, hi Jen. The second function I wanted to mention here is filter, which is also another higher order function that works on lists, and it builds a new list based on a filtering function. So the higher order function in this case accepts a function from A, which is the type of the element in our list, and returns always a Boolean value as a result. And if this Boolean is true, then this element will be in the filtered list. If it's false, it will be discarded. Okay, and then we give it our list of A's, and we get back a list of A's, the same type, only certain elements dropped which don't satisfy the predicate or the filtering function, right? So we can also define this function with list comprehensions. We take in the filtering function, we take in our list as XS, and now our list comprehension will take the value X in the new list, where X is taken from this XS list, but only if the application of the filtering function to X equates to true, right? So that's the filtering function, and we can check some examples here. So the important note is that this function that we take in always must return a Boolean to be a valid filter, unlike map. If we filter square GT100 on this list, then we remember that 7, 8, and 9, and 10 are going to equate to false for this function. So those elements will be dropped, and then we only get 11 and 12, which satisfy this predicate. We can also filter out using the odd function to get all the odd numbers. So we get 1, 3, and 5. We can use lambda functions as the filtering functions as long as they return a boolean. So here we have a lambda function that takes in an argument x, and the function body is defined as if the length of x is greater than 2, then it's true, and if it's not greater than 2, it's false. So a, the length of this is 1, it's false, and abc, the length is 3, so this is true, and in the new list we get only the abc string back. Here is another example of using a lambda function and the pattern matching of xs, where we take this pattern and we say if the head of the list is equal to a, then that's the predicate, right? That's true, and if it's not, it's false. So in our Cardano ADA list, we only get back ADA in the new list because ADA starts with A and Cardano starts with C. That's the end of this presentation. We covered the basics of list comprehensions and higher order functions, and now we'll go into the practical part where we'll try to solve some examples using these concepts. Let's start with list comprehensions. So we said list comprehensions are a way of defining lists in Haskell through existing lists or other lists in general. So we can define here a static list, let's call it L1, and it will have a type of integer, and L1 will simply be a list of 1 to 5. And now, for example, let's use the example from the presentation that dealt with even numbers. So if we want to say evens of this L1 list, it will also be a list of integers, and we will simply define. So what we want to define is a list of even numbers created from this list L1. So we can use the list comprehensions, and the syntax is the generator, in this case I call it x, then from which lists the x is generated, right? So we have x is taken from the list of xs. In general, this is the pattern, but here we can use our static L1 list that we defined here, so it will be available here. And then lastly, we could have another list here, more lists to generate the new values from, but here we don't want to. We just want to end it with a guard that is a predicate that the generator must satisfy. The element from the L1 list must satisfy in order to end up in the new list. So in this case, this is simply even x, the number must be even, right? So we can check this in GHCI if we load our where am I? Load session 5 HS, and so we have access to L1, which is simply the list, and we have evens from L1, which is just 2 and 4. Let's do one more example of list comprehensions. Say a function that counts the number of times a character appears in a string. Okay, so we'll call this function count, and it will accept a char, a character. It will accept a string, a list of characters, and it will give back an int, which is the count of the number of times that this character appears in the string. Okay, so we want to use list comprehensions or list comprehension. And what do we want to do? We would like to first create a new list that contains only the characters of the previous list that match our character, right? So we have two arguments here, the char argument, which we'll call x, and the string argument, which we'll call xs, right? So if we create a new list of multiplied characters x, we could do that as, so we cannot use the generator x here because that's the name of the argument already. So we can use x prime, and so x prime will be taken from the list xs, and it must satisfy a predicate, right? We only want to take the character from the list if it matches the character we are looking at, right? So, and that is x. So x must equal x prime. Now, I'm not sure if the okay, this is right. So it says couldn't match expected type int, right? Because our function should return int, but this is a list of characters as it is. So basically, we took all the characters that match our character we're searching for, and we have a new list of just those characters. So we simply need to check the length of this list to know how many characters there are in there. Okay, so let's test this out. For example, so we have count, and then we have a character, let's say s, and how many times does s appear in success? 3 times. Okay, so that seems correct. Note that we didn't do any to lower or something, so lowercase s is not equal to higher, so we capitalize our list, we'll get back the count 2, right? And if we search for the capital S, we'll get back 1. So we just look at the exact character, and it's case sensitive in this case. Besides list comprehensions, we also learned about higher order functions, and specifically 2 higher order functions, map and filter, for working with lists. So we had some examples of a map for such as multiplying the numbers in a list by 2 and so on. Let's write some functions then here. I'll just call it f1. That will be just a static value of integers. So the example from the presentation was, so if we map, and remember we can check the type signature of map. So higher order function accepts a function as an argument, a function from a to b, accepts a list of a's and returns a list of b. So it applies this function from a to b to each element a of this list to return a new list with the values generated from the function application. So we can use curring to do multiply by 2, and then apply to a list of 1 through 5, and now this all the elements in this list will be multiplied by 2 for this expression f1. Right, so we get 2, 4, 6, 8, and 10. So we can also map other functions, of course. For example, there is a negate function that negates numbers, so from positive to negative and vice versa. We can define a function, let's just call it f2, that accepts a list of a's and gives back a list of a's, and we'll use a type variable a here with a class constraint of num. So because negate can work with both integers and floating point numbers. So this function takes in a list, we can call it xs, and it maps the negate function to each of the elements. It maps it to xs. Now the editor is telling me probably, yeah, I can use ETA reduction, so I don't need to have xs on both sides. I can remove it like so. So the function map negate accepts another argument, a list of a's, and this will work fine too. So if we reload and then f2, we check the type of f2, it's what we set in the signature, and f2 of our list 1 to 5, for example, is minus 1, minus 2, minus 3, and so on. So that's the map function. And we also talked about the filter function. For the filter function, we can make an example. I'll put it below this one. So we can write the count function with the same functionality, but using a higher order function filter instead of list comprehension. So we'll call this one countf, and it will do this. It will have the same type signature, right? We are looking at characters in a string to give back the count. And so countf, what we want to do is basically the same thing. We'll still have to count the length, but instead of this list comprehension, to generate a new list, we can filter the list instead. So if we remember the type of the filter function, we have another function from a to a boolean, and then accepts a list of a's and returns back a list of a's. So the function that filter accepts must return a boolean. So we have filter, and then our function that this function will still be applied to each element, and if the function application to the element results in true, then that element will be included in the filtered list. If it evaluates to false, then it will be excluded. So our function that we want to use is that, and we'll use currying here. So let's have the same argument names for countf, so x and xs, and what we want to check is that x is equal, right? So to each element we want to apply this function x equals the element of the list, and then we apply that to xs, and I think that should be fine. Okay, so of course the type is not right because we expect the type int, but this is just a filtered list, so we put this in brackets and then use again the length function, and now we should be fine. So if we reload and then we say countf of the character s again in success, we get back 3 as well. So this is an example of using the filter function instead of list comprehensions. Okay, now let's get into the katas for this session. I prepared 5 of them, and we'll start with this one, sum positive. I think it's a simple one to start with. This function should work the following way. You get an array of numbers and return the sum of only the positive numbers, okay? If there is nothing to sum, the sum is default to 0. Okay, I don't think we'll need to worry about that last time, but let's see. So we want, in this example, 1, minus 4, 7, and 12, we want to ignore 4. So basically, we can filter, or we can use list comprehensions. Both is okay. Let's do it with list comprehension since we started with that. So we want to create a new list of only the positive numbers. So we can use our general syntax of x, where x is taken from the list xs, and it has to satisfy a predicate, and that predicate is that it has to be greater than 0 so that it's a positive number. So x must be greater than 0, and now we have our filter list, and all we have to do is sum it up. So if we now load, we are session 4, then session 5, sorry, then katas and sum positive, and if we have positive sum of an empty list, we get 0, which is correct. And if we have let's use the example 1, minus 4, 7, and 12, we get 20, which is also correct. The next one will be largest elements. Another simple one. So write a program that outputs the top n elements from a list. Example, largest 2, so 2 is the n, and then a list. And then the results should be 6, 7 from this list. So it seems that it also must sort it. So because here it's 7, 6, and then in the results 6, 7. Okay, we will say that it has to sort them as well. So how could we do this? If we imagine here in this example, what we first can do is sort the list. So we have 1, 2, 3, 4, 5, 6, 7. And then we just want to take the last n number of elements. So 2, in this case, 6 and 7, right? So basically this will be a combination of sort applied to the list xs, and then we can compose this function with the drop function, right? So we want to drop all elements except the last n. And the trick is then how many elements do we need to drop if we know n, and obviously also we know the list, so we know the length of the list. So to drop, in this case, we want to drop 5 elements, right? The length of the list is 7 and the n is 2, right? So 7 minus 2, the length of the list minus n is the number of elements we want to drop, right? So length of xs minus n is the number of elements we want to drop. And now we have to load largest elements, and we can test with largest. So we can use this example, largest 2, and now we get back 6, 7. So we could have done this in a different way, of course, like we could sort it, then reverse it to get the highest elements in the front, and then instead of drop, use just take n. But that would then give us back the result 7, 6 in this case. So we would have to reverse that final list again. Anyway, always a lot of things, a lot of ways to do the same thing. In this case, this is our solution for now. Moving on to the next kata, invert values. Okay, yeah, this is gonna be the same as I gave in the example for the map function, but okay. So given a set of numbers, return the additive inverse of each. Each positive becomes negative and the negatives become positives, right? So this is our negate function, basically. So a list of 1, 2, 3, 4, 5 is all the numbers negated, and here if we have 1, then it turns into -1. If we have -2, it turns into +2, and so on. Okay, so we basically wrote this function at the start of the session, and we just want to map the negate function that will negate a number. So if it's positive, it will be negative. If it's negative, it will turn into positive. We map the negate to array, and we can also use ETA reduction. We don't need array here, so we can define invert as just the function map negate to the argument it receives. And if we load session 5 katas invert values, invert values, and then we invert, say, this example, correct. This one is more interesting since it contains both positive and negative. So 1 becomes -1, -2 becomes 2, and so on. So you can see the negate is applied to each argument and a new list is formed. The next one will be a bit more interesting. It's called disembowel, and it says the trolls are attacking your comment section. So what we want to do is remove all the vowels from the trolls comments. Okay, so we need to write a function that takes a string and returns a new string with all vowels removed. In other words, filters a list of characters, a string. So for example, this website is for losers, lol, would become this website for losers. For this kata, y isn't considered a vowel. Okay. So we can see we go from this list to this list, which is basically the same, except some characters have been filtered out. So obviously we can make use of our higher order function filter. We can also do it with list comprehension, but since we already use that, let's use filter here. So we will want to apply the filter function, and then we have to apply some function and apply it to our string, and we need to define this function. So our function should filter out vowels, right? So we can define it here in the where, and we'll call it, so we basically want to filter for not vowels, right? If it's a vowel, we want it filtered out. If it's not a vowel, then it stays. So we can call this function is not vowel, and is not vowel will be defined here. It will accept a character. Also, we can write type signatures for functions in the where clause as well, right? So we can say it accepts a character. We know that it must return a boolean since we're going to use it with the filter function, and is not vowel then accepts a character C, and then what do we want to check? That it's not a vowel. So the vowels are A, E, I, O, U, right? Those are the vowels. Y is not considered a vowel. I didn't really know it is a vowel. But anyway, A, E, I, O, U, those are the vowels. So we want to check that this character is not in this list, right? It's not any of these characters. So we saw the function elem in Haskell, which checks whether an element exists in a list, and here we want to use not elem, which is the same function but negated, right? So we want to check that C is not an element of the vowels, and we have to deal with case, right? Because we could have a vowel that's capitalized and then it will not. Oh, well, we can either deal with case in two ways. We can spell the vowels here in capital case as well. So now this is okay. Okay, we can refactor it, or we can say two lower C, compose these two, and then apply it to our vowel list. I will do it this way. Okay, yeah, so it's saying we can write it in a different way, basically two lower C, and then using our infix operator, not elem. Yeah, variable not in scope, two lower. So two lower is actually, oh, this got filled in, right? Because I auto-completed something. We don't need that. Two lower is actually in this package called data.jar. So we can import this function. It simply accepts a character and puts it into lowercase. So something is wrong here. I guess the application operator is not needed here. So to lower c is not an element of the lowercase vowels. Also here we can remove string on both sides. And that should be it. So we can load this and vowel, and we can test it with this. So this and vowel, this website is for losers, and this website's for losers too. It works fine. Okay, it's time for our last kata for this session. It's called Alphabet War, and it says there is a war and nobody knows it's the alphabet war. There are two groups of hostile letters, the left side letters and the right side letters, and we need to write a function that accepts a fight string consisting of only small letters and returns who wins the fight. So we accept a string and we return a string. So when the left side wins, return left side wins. Otherwise we return right side wins, or if it's a tie, then we return let's fight again. Okay, left side letters and their powers, right side letters and their powers. The other letters don't have power and are only victims, so I guess their power is 0. And okay. So what we could do is write a function that maps a character to a value, to an integer value such as this. So we can use, for example, minus for the left side and plus for the right side. We will then create a new list. So for example, this list z would, after a mapping our function, z has 1, so it will become a list of 1. In this case it would be like z is 1, then d is 2, then q is 3, but give me a left side. M is okay 4, and then the left side w is 4, so in left side it will be minus 4. Okay, and then if we then sum that up, we get the score and we can decide which side wins, right? So we can write the high level with a guarded equation. We will have some score that will calculate, and if that score is greater than 0, then we will say, so what do we say? Right side will be positive, so right side wins. Okay, if the score is less than 0, then we will say left side wins. And otherwise, we will say let's fight again, right? Okay, so that's like our how higher level how our function should work. And then we need to say where score is going to be, so the sum of our new list that we get by mapping our new function, which we also didn't define yet. So sum applied to this new list that we'll get by mapping the, what should we call this function? For example, get value from character applied to, so this xs that we get as the string. This looks okay. And so finally score should be just an integer value. What we don't have is the get value function. And get value is a function so it will be mapped to a list of characters, so it will be applied to each character. It will accept a character and it will return an integer. Right, and now how do we define that? Well, since these are just arbitrary values, 4, 3, 2, 1, we don't have much choice but to list them all out. Right, so we just have to list each character one by one and assign it a value. So we can use pattern matching here. Let's do the left side first. So it's gonna go something like this. So get value w is going to be left side, we said minus, so -4. Then get value p, b, and s. So there will be -3, -2, -1 respectively. And then we'll have the same thing duplicated for the right side. For the right side value, which are mqdz. Or mqdz, and they will have positive values. 4, 3, 2, 1. 4, 3, 2, 1. Okay. We also need finally the wildcard, which is any other character, and we know that that value will be 0. So I actually think this is done, right? So we get our list of integer values by mapping this function to our original list. We sum it up, and then if the numbers are positive, the right side one, if negative, the left side one. Did I get it right? Yeah. Yep. Okay, so let's load this up. Alphabet war. And then we have the function alphabet war. Let's use this string. Let's fight again. Okay, that's correct. Z, S. Right side wins. Okay, correct. W. Left side wins. Correct. Okay. That's it for the katas for this session, and that's it for this session. We explored list comprehensions and higher order functions. Thanks for watching, and see you in the next video.